Hey there, another edition of Kung Fu Physics. We're working our way through the practice physics GRE problems one at a time. Tonight I have problem 75 off of the 1986 exam for you. It's a mechanics and or astrophysics problem, depending on how you look at it, regarding the orbit of an object in a gravitational field. So let's go ahead and start right into it. I glance at the answers quickly. It's obviously some constants multiplied by r sub e. That's what I'm going to be picking from. Don't waste any time with those really, and then move on. Number 75. The period of a hypothetical Earth satellite orbiting at sea level would be 80 minutes. In terms of the Earth's radius, r sub e, the radius of a synchronous satellite orbit, period of 24 hours, is most nearly what? Now, this is certainly something that you could have memorized. If you're interested in things like satellites and astronomy and things like this may be something that you had come across before. I mean, I do a fair bit of stargazing and astronomy stuff occasionally, and I will sometimes spot near synchronous orbit satellites. They're very cool. They kind of just move very, very slowly. If they're tumbling, they actually flash. So anyways, I'm babbling, but what I'm saying is this is something that I would be interested in, and I'm kind of ashamed that I didn't know the answer immediately. But, you know, I refreshed it after I did this problem. Maybe I'll remember it from now on. But something like the orbit that a geosynchronous satellite orbits planet Earth is something you could memorize. But let's do the problem. The assumption being that we did not have that little bit of trivia memorized. So you use Kepler's third law again, and this is the second problem in a row that I've done using Kepler's third law. So you just you remember that the period of the satellites is proportional to radius cubed. And when I say radius, I'm actually talking about it's the semi-major axis of the ellipse if it's an elliptical orbit. For most of the physics GRE problems, it simplifies to a circular orbit. So you can just use r. That simplifies to r. Now what this is saying in effect is that there's some constant there, and that's really all we need to use to solve this problem. Okay, so let's go ahead and do that. So t squared equals k times r cubed. And then we are going to get k first by giving the information that they tell us. They say 80 minutes. Now before I write 80 minutes, what I would see that in my head is as 4/3 an hour, because I know we're going to use 24 hours later, and I don't want to convert 24 hours to minutes. So to me, that is easier. So that's my period, 4/3 of an hour. That's squared. That equals to some constant k multiplied by r sub e cubed. Okay, so from there you get k, and k is just 4/3 squared over r sub e cubed. Okay, now we're going to use that same k because the physical situation is the same. It's the planet Earth, and the k will be the same proportionality constant in the second situation. When we talk about, rather than 4/3 an hour, we're talking about 24 hours. Squared is equal to k times r, and I'm just going to use r cubed, and that's the radius that we want of the geosynchronous orbit. So I'm just going to plug in my k there, and so I get 24 squared equals 4/3 squared over r sub e cubed times r cubed. And I solve for r cubed. So I end up just doing the algebra from here, I get 24 times 3 divided by 4, all of that junk squared, right? Divided by r sub e cubed equals r cubed. than I want to solve for r. And at this point, this is where it helps to use your little bag of math tricks and think ahead. When you're looking at this, think ahead, see what little trick can you do to solve that easily, right? Because you're going to need to take the cube root there, which is, I think, the biggest pain in the neck of this problem. So I don't know of any specifically math trick that I would use there. Basically 24 divided by 4 gives me 6. 6 times 3 is 18. I get 18 squared. Right? And then I need to take the cube root of 18, and that's kind of a pain in the neck. I would like to say that I have 18 squared memorized. That's something on my list of getting, taking the square of numbers really quick, and something like, up to 20. But I didn't. I just wrote it out. I just wrote it out and did the little calculation, and that was 324, which I remember now. Hopefully I'll keep reviewing that in my head and go back and make sure I can quickly square numbers like, 15, 16, 17, 18, 19. Just if you memorize the squares for all that, then when you come up with something like this, it's that much easier, right? And did I make a mistake here? I guess, where did I make a mistake here? I think I made a mistake because I put this on the bottom here. And this should not be on the bottom here. I'm very sorry. Let me just erase that. Pretend like that was not on the bottom, because we're not over here, we're multiplying over, so oops. So that's not on the bottom. So anyways, I just need to take the cube root, or raise this to the 1/3 power, and I don't know of a great way to do that. I mean, I'm sure there's some Taylor series approximation thing that you could do. At this point, I wouldn't even mess with that. I would look at the answers at this point. I would look at the answers and figure out what closely resembles the cube there, and I might even write them out. So, I know it can't be 18 because I squared 18 to get to 324. So I know it can't be 18. So I'm looking at 7 or 3. I can do 3 in my head. I can do the 3 cubed in my head. So I land on 7, and if I wanted to be a little safer, I could do that. I could just say, 7 squared is 49 times 7, and I could multiply that out, right? And it's close, 343. I'm in the neighborhood. I would feel okay about that, and that's what I would do. I would pick B, about 7 times the radius of planet Earth, and that is, if you ever look up something about geosynchronous satellites, like the kind that bring your satellite TV down to you, that's where they'll be orbiting. Is about 7 times the radius of planet Earth. So it's an interesting problem. I really did babble on about that. I think if you're pretty sharp with Kepler's laws and your arithmetic, you could smoke through this problem pretty quick, in about 2 minutes or less, I would say. So I'm trying to think if there was anything else I had to say on that. I don't think so. And I'm droning, so I'm just going to wrap that up. That is number 75 off of the 1986 exam. So as always, thank you for watching. See you next time.